Okay, let's get started. Welcome to the session on the Best Paper Awards. So the first winner of the Best Paper is Lower Bounds for Maximal Matchings and Maximal Independent Sets by Alkida, Balliu, Sebastian, Brandt, Juho, Hirvonen, Dennis, Olivetti, Mikaël, Rabie, and Jukka, Suomela, I don't know. And Sebastian will speak.
Thanks very much. Yeah, I also don't know how to pronounce the name correctly, but some of these guys are sitting over there in that row, Alkida, Dennis, and Mikaël. And actually, Dennis was supposed to give the talk today, but he got sick and had to go to the hospital, and now he's very well drugged, if you take a look at him. So actually, he is in no shape to give the talk. I know that he would have loved to give the talk, so I'll try to do my best, and all the credits for the slides goes to him. So let's start. So, maybe I should go back. So apologies for omitting some maybe important word here that is distributed. So we want to show lower bounds in the distributed setting for maximal matching and maximal independent sets. And I'll tell you in a second what the exact model will be. But let's first quickly recall these two problems of interest. So maximal matching is just the task of finding a subset of the edges such that no two of these edges are adjacent, and the chosen set is inclusion maximal. So we cannot add any further edge to the set without violating the non-adjacency property. And maximal independent set is basically the same problem, just we are looking at vertices, or as we say in the distributed setting, nodes instead of edges. Okay? And in the centralized setting, we have very simple greedy algorithms for these problems, which just work as follows. For maximal matching, we go through all the edges in arbitrary order. And each time we process an edge, we just put it into the matching if none of its incident or adjacent edges are already in the matching. Otherwise, we leave it out. Okay? And this will very easily gives us maximal matching, and the same process works for maximal independent set if we just look at vertices instead of edges. Now, from a distributed perspective, we would like to know how fast can we do such finding a maximal matching or maximal independent set. In the log model, I will explain in a second. And one thing to consider here is that maximal matching is actually a maximum independent set on line graphs. So it's a special version of maximum independent set. So all the lower bounds we prove for maximal matching will immediately also imply for maximum independent set. So we will just look at maximal matching since we are about to prove lower bounds. So the setting we will consider is the local model of distributed computation. In the local model, we usually want to solve some graph problem, but the nodes doing the actual computation are the nodes or vertices of the input graph. Each of these vertices hosts a processor, and over the edges of the input graphs, these processors are allowed to communicate. The actual computation proceeds in synchronous rounds, and in each round, two things happen. First, each node sends an arbitrarily large message to each of its neighbors, and then when the messages arrive, each node is allowed to perform some arbitrarily complex local computation. Each node has to decide at some point in time that it terminates, and then it has to output its local part of the global solution to the problem. So for example, if the problem is to find a proper vertex coloring, then each node has to output a color, its own color, such that the induced global coloring is indeed a proper vertex coloring. The time complexity of such a distributed algorithm is just the number of rounds until the last node terminates and gives its output. Okay? And there's some other constraint, which is that nodes are assumed to have unique numerical identifiers, but this is just to make sure that we don't get any impossibility results based on the symmetries in the graph. Okay, so let's try to see how we can get an algorithm for maximal matching in this model. And let's make things even a bit simpler. So let's assume we have some additional assumptions, such as that we are actually in a bipartite graph. So we have white and black nodes. The nodes know their own color, input color, so they know on which side of the bipartition they lie. And we also assume that the input graph will be a delta regular graph, where delta is the maximum degree of the graph. And one last assumption is that actually we assume that each node has a port numbering. So for each node, the incident edges are numbered from 1 to delta in some way. Now, how fast can we find maximal matching in this setting? There's a very simple proposal scheme to get such a bound, such an algorithm. This goes as follows. In the first round, each white node proposes via port 1. Okay? That means it sends a proposal to the neighbor at the other end saying, well, I would like to match to you via this edge. And then the black nodes will respond. If a black node only gets one proposal, it will accept this proposal. If it gets more than one proposal, it will accept exactly one of those proposals. Okay? And it will break ties by just taking the proposal that comes in via the smaller port. So in this case, these two proposals will be accepted, and the other two will be rejected. And then in the next round, well, white nodes are not matched. Edges via which a successful proposal was sent, they will be added to the matching. Now in the next round, each white node that isn't matched so far will send a proposal over the next port, port 2. And again, the black nodes will exactly one of these proposals, except if they already have a matched node, a matched edge. Then they don't do anything anymore. Okay, in this case, the upper proposal will be rejected and the lower proposal will be accepted. So this edge will be added to the matching. And then in the next round, well, every white node that is not matched, so only the white node on top there, sends another proposal over the third port. And in this case, since the black node is already matched, it will reject this proposal and this edge will not be added to the matching. Okay, and it's very straightforward to check that this process actually results in a maximal matching. And the question, of course, is how fast did we get this? Now, if we think about it, each white node sends at most one proposal over each edge. So at most delta proposals are sent per edge. So we need delta rounds for sending the proposals. And each black node answers at most via once via each edge. So also for the answers, we need at most delta rounds. So we can perform the whole thing in O of delta communication rounds. Of course, the question now is, can we do better? Can we be faster? And, well, there are, I guess, a number of ideas that one could try to use to make this faster. For example, sending multiple proposals in one round and then trying to deal with the rising difficulties. But actually, as we show, this is optimal. So this simple algorithm is the best you can do in terms of dependency on the maximum degree. Okay? So much for introduction. Now let me give you a picture of what the state of the art was and is now. And in the distributed setting, we often have runtimes that are the sum of a function in n the number of nodes of the graph and delta the maximum degree. So we will display all these upper and lower bounds as a function delta plus a function in the number of nodes. And, well, the first two bounds in the late 80s and early 90s are these two. There's a log n randomized upper bound for maximal matching, and it is impossible to go below log star n, both for randomized and deterministic algorithms. And log star n is just the number of logs you have to take to go down from n to below 1. Then in the end of the 90s, the first polylogarithmic deterministic algorithm was found and subsequently improved. And also we have a deterministic algorithm that runs in time delta plus log star of n. On the lower bound side, we have the famous lower bound by Kuhn, Moshiboda, and Wattenhofer that tells us that you cannot go simultaneously below a dependency of log divided by log log in the maximum degree of the graph and root of log divided by log log of the number of nodes of the graph. Okay, and well, there are two randomized algorithms that come, well, somewhat close at least to these lower bounds, and those are randomized algorithms running in roughly log delta plus polylog log n time. Now, the natural question to ask is, can we get the best of both worlds if we, for example, look at the algorithm by Fisher and the algorithm by Panconesi and Rizzi? Can we, for example, get an algorithm with runtime log delta plus log star n? Or if that is not possible, can we at least get some well, maybe smooth transition from the one algorithm to the other. And how would this curve look like? So as we show, neither of those is possible. Actually, if you want to be sublinear in delta, then the dependency on n immediately has to be at least log divided by triple log for randomized algorithms. And for deterministic algorithms, the picture looks even worse. If we want to get better than a linear dependency in delta, we have at least a log over log dependency in the number of nodes. All right, so here are these two bounds, and actually the main difficulty in proving this bounds is showing the lower bound in delta, this linear lower bound. If we have that, then basically by choosing the right graph class and, well, tuning the parameter delta to be, well, either log divided by log for deterministic or log divided by triple log for randomized algorithms, we can lift this bound, this linear delta bound, to the bounds we see here. So let me try to give you an idea of how the proof goes to prove this linear delta lower bound. Let's do a proof by contradiction. We want to solve, we assume we can solve maximal matching in little o of delta time. And the first step is to show that this implies that we can solve another problem called root delta matching in little o of root delta rounds. And root delta matching is basically the same as maximal matching, just each node that is matched is allowed to be matched to up to root delta neighbors. Okay? If you're an unmatched node, all of your neighbors have to be matched. But if you're a matched node, you can have up to root delta of your incident edges to be in the matching. The next step is to show that this implies also a little of root delta around the algorithm for this problem we have on the left. And what is this problem? Well, it comes from a parameterized family of problems that contains problems that are relaxations of maximal matching. So each of these problems in this class has two parameters, x and y, and these two parameters basically tell you how much these covering and packing constraints of maximal matching are relaxed. Okay? The larger x and y are, the more relaxed these constraints are, so the easier the problem gets. In particular, for example, this problem with parameter root delta and 0, this is a slightly weaker version than what we know as this root delta matching. Okay? And the relaxations are not very straightforward relaxations, but they have a very useful property. And one, well, instance of this property is that if we start with a problem with parameters root delta and 0, and we assume that this problem can be solved in sub-root delta time, then one can show that actually for the same problem with somewhat higher parameters, we can solve the problem in 0 rounds. Okay? For a more relaxed version, we can solve it, must be able to solve it in 0 rounds. And now we complete the proof by contradiction by showing that even though we have relaxed the maximal matching quite a bit, the parameters are not large enough to allow a 0-round algorithm. So we get a contradiction. Okay. And well, the most interesting part, in my opinion, is between line 3 and 4 to get from this little of root delta algorithm to the 0-round algorithm. And the technique we use for that is a technique called round elimination, a relatively young technique, where the idea goes as follows. So assume you are given a problem P0, and assume that is solvable in some number T of rounds. Then if this problem P0 is of a certain form, in particular if, well, you can describe it, roughly speaking, via local constraints, and maximum matching is one of these problems, then you can construct a new problem, P1, that you can solve 1 round faster. Okay, and you can apply this argumentation iteratively, then you get a problem P2 that is solvable even 1 round faster, and so on until you do this T times and get to a problem PT that must be solvable in 0 rounds, under the assumption that the original problem is solvable in T rounds. Now you just have to show that this problem PT is not solvable in 0 rounds, and then we know that our original problem P0 cannot be solved in T rounds. And by that we get a, well, T minus 1 lower bound for the original problem we are actually interested in. Now, this year, we showed that actually this problem sequence P0, P1, P2, and so on can be generated in a fully automatic way. So we have a just mechanical way to take this problem P0 and generate this whole sequence of problems. The only problem is that the descriptions of these problems grow very rapidly, or can grow very rapidly. And they can grow so fast that even for small indices, it's basically not feasible anymore to look at the problem and try to see any structure there. So one somehow has to find a way to get these problems somehow easier to look at least. And well, I guess that is one of our main contributions, that we show that we can transform this automatically generated sequence into a sequence that has problems where the description complexity does not grow in each step, where we basically have one complexity, description complexity with which we can express all of these problems. And well, I would love to show you more about this technique, but even though the problems are somehow concisely explainable or describable, I mean, here on the lower half of the slide, we have actually the description of one of these problems with parameters x and y. It just would take too much time to, well, make sense of this problem. One can make sense of this problem, but it would take a lot of time. So let me just say that what we show in the main lemma is that if one can solve this problem with parameters x, y in a number t of rounds, then we can also solve the problem where the first parameter is increased by 1 and the second parameter is increased additively by the first parameter. Then we can solve this problem in t minus 1 rounds. So if one then, well, uses this round elimination framework and does the math, then this will result in a root delta lower bound for, well, these parameterized problems for small parameters, and this in turn will give us a linear delta lower bound for the original maximal matching problem. Okay, so this will give us a lower bound for setting where we only have deterministic algorithms. And there's also some other detail I didn't tell you about, that nodes have to be assumed to be anonymous for this to work. So this is not a bound that directly applies in, say, the deterministic or randomized local model, but the bounds we get can be lifted to both the randomized and the deterministic local model. For randomized algorithms, there's a way to incorporate error probabilities explicitly into this round elimination process, and then one can use basically the randomized bounds one get to lift them to higher deterministic bounds. Okay, so additional techniques are required to make the bounds work in the models we're actually interested in, but this, well, can be done by using some known techniques about the relation of, well, randomized and deterministic complexities for distributed problems. So to conclude, we proved the lower bound of linear and delta for maximum matching and maximum independent sets. And we showed that these lower bounds can also be transformed into good lower bounds with respect to the number of nodes of the graph. In particular, we also showed that this simple proposal algorithm that gives you an O of delta algorithm cannot be improved even if we use randomization or send huge messages to our neighbors. So maybe let me finish with an open problem, or I would say a huge open problem, maybe the largest problem open in this vein. So we have seen that for maximum matching and maximum independent sets, we have this centralized, very simple greedy algorithms. But we do not have a distributed algorithm that is as efficient as we would like. So for delta plus 1 coloring, we also have a very simple greedy algorithm that solves the problem in a centralized setting. But for the distributed complexity, we have a huge gap between the lower bound and upper bound, even larger than we had before for a maximal independent set or maximum matching. So it would be very interesting to see whether, well, we can get for this problem a better distributed algorithm, a fast distributed algorithm, or whether maybe some techniques that we have seen here might be applied to also lift this lower bound, which currently is at log star n, so really low, to lift this to a higher lower bound. And, well, that's all I have. Thanks for your attention.
questions?
Excuse me. A couple of implicit questions.
Okay.
First, well, your results are very interesting, which is theoretically what it's about, right? But why take why take matching in a bipartite graph, which is deterministically easiest imaginable problem in combinatorial optimization? How does it depend on bipartiteness? Why not matching in a general graph? Indeed, for that matter, why not set packing? Second question: solving these problems is so easy deterministically, and computers are so fast that do you ever actually have need for these methods that are don't give the optimum result? So, do you understand my two questions?
Yeah, I hope so. So for the first question, I guess one could consider the problem of non-bipartite graphs, but these upper bounds we saw, for example, this delta plus log star n upper bound, that does not depend on whether the graph is bipartite or not. It also works in non-bipartite graphs. So basically, we cannot improve our lower bound in that respect. We just use to prove it already for bipartite graphs because it works and it's easy to prove it in that way.
You're actually using the bipartiteness to get your lower bound.
In some sense, the technique we use works in some sense better if it's a bipartite, if we consider it on bipartite graphs. But of course, I mean, if we prove it on this
upper bound if it's bipartite, of course.
Sorry?
Are you getting a better lower bound or better upper bound using bipartite?
We use bipartiteness to get a better lower bound. And of course, this lower bound then also applies to general graphs. And also in general graphs, we have this upper bound of delta plus log star n. So there we cannot.
Let me see if there are any other questions. Yes.
A simple question connected with the last question.
Yeah.
So suppose you keep on increasing the number of colors you are allowed to use, not the delta plus 1. Suppose you keep on increasing. At what moment you can reach the delta plus 1?
At what moment?
So suppose you keep on increasing the number of colors you are allowed to use.
For coloring, yes.
For
okay.
coloring. For what number or function that suddenly you can go below the degree?
So there is a nice algorithm by Lineal from, I think, 87. There he shows that for a delta squared coloring, that you can get in log star n time in any graph.
I see. The delta square
Yes. So basically, if you can reduce from delta squared to delta plus 1 colors very quickly, then you have solved everything you want. Yes.
Okay, let's take remaining questions offline, and thanks, Sebastian, again.